A little bit of background about Euclid and the Pythagorean theorem. So we mentioned Hippocrates last time. Euclid came after Hippocrates by about 100 years. And Hippocrates, remember, wrote an early version of the Elements, which was basically a systematic organization of geometric ideas. Remember, the Greeks had a particular obsession with the intellectual realm, okay? They sort of saw the intellectual realm as, you know, there was some kind of spiritual connection there. The physical, on the other hand, was something that they saw serious problems with. They actually saw other cultures as being fundamentally flawed, as having focused too much on the physical and being anchored too much in the physical to the point where they were only interested in applications and whatnot. The Greeks saw that as a giant mistake. And as I mentioned before, that caused them to have this kind of incorrect notion at some point of the physical being bad and the spiritual or intellectual realm being good. And those two things being at war with one another. That's not a biblical idea, okay? But Euclid is kind of known as the great organizer of the Greek system of thought, okay? And the way he did it is he started the elements with a bunch of definitions and axioms and common notions, and then eventually postulates. Okay, well, in the postulates, a lot of them were pretty basic concepts that didn't really require proof either. But then once he had kind of laid out the foundation, he started in on the propositions. And then he kind of focused at some point on the idea of parallelism and the like. The stuff that we're talking about right now is basically all going to belong to book 1 of the Elements. Now, there's a lot more than just one book in the Elements, but the things that we're going to be talking about today really kind of reside within book 1. Okay, I am going to show you. So we're going to obviously look at Euclid's proof of the Pythagorean theorem, but we're also going to have a peek at some other proofs that have come down throughout history. I'm not going to ruin it for you. There's pictures there. You can go over to Chuck's and play around with those pictures, and I'm telling you the proofs are residing within those pictures also. There's going to be 3 pictures, one of which came from James Garfield, if you can believe that, former president of the United States, okay? Pretty interesting. Okay, so Euclid is thought of as the father of geometry. Again, mathematical proof, as we know it today, is largely due to kind of his general approach and argumentative style. Plato was a huge influence on Euclid's thinking. And there's an interesting, this is actually in the book itself, in chapter 2, talks about how when you entered Plato's academy, there was this sign over the entryway that said, "Let no man ignorant of geometry enter here." So just kind of this idea that geometry was at the center of what the Greeks were trying to do intellectually, okay? There was something beautiful about it. It wasn't just arithmetic, okay? There was arithmetic, and a lot of other cultures had tended to focus almost exclusively on arithmetic. But geometry seemed to pull in this idea of logic and in proof, and there was just more of this abstract realm of ideas that that really caused the Greeks to elevate geometry to this place in their culture. Almost all Greek mathematicians following Euclid had some connection with his school in Alexandria. Okay, nice picture of Euclid there. Probably not accurate, but still a pretty cool picture nonetheless. Okay, so what about the Elements specifically? Well, it was written in Alexandria about 300, right, so this is 300 BC. You guys remember when Hippocrates was doing his thing? Yeah, right, so it's about 5th century, you know, so this is 150 years or so after Hippocrates. The Elements consist of 13 total books on mathematics and geometry. Now, there's a fair amount of number theory in there, okay? In mathematics and actually in philosophy in general, we talk about things called axioms, okay? And Euclid's approach the sort of the approach itself, the axiomatic approach, is largely due to the elements and the way that Euclid laid things out. Mathematicians today still do this. Okay? So the axiomatic approach first gets down the things that we won't be arguing about. Sometimes that happens to be like an undefined term. Okay? I mean, if you think about it, I can't define every term that I use because eventually I'm going to run out of words if there's going to be like an infinite regression. Okay? So you have these undefined terms, you have definitions, you have postulates, and 5 common notions. Now the 5 postulates, I might, instead of calling those postulates, I might recall those axioms, to be honest with you. Okay? Because they're things that he didn't try to prove, and they're just basic items that that he saw as kind of things that were almost self-evident. Okay? So overall, in the 13 books, there's 465 propositions that he proved from this basic axiomatic set. Now, what you do is when you have these axioms, you start building, and eventually, once you prove something, that becomes part of what is known. And that gets drawn into the collection of things that you know to be true. And then you can then use that to prove further things, and then those get drawn in, etc. By the way, the Elements, and this is largely agreed upon. The Elements is one of the most scrutinized books in all of history, okay? Both positively and negatively, honestly. And Dunham actually remarks that only the Bible has been more scrutinized over time. Okay? And almost all the propositions, even though there were some problems with like things that Euclid was assuming but didn't realize he was assuming them, because just of a lack of general sophistication that only could come with, centuries more time of development of mathematics and notation and whatnot. Nonetheless, almost all the propositions in the Elements are known to be true, okay? Even though we might have thought of some of the proofs or some of the underlying principles to have been missing, all of those propositions have stood the test of time, almost all of them. So the definitions, okay? His definitions were kind of the basic foundations of what we call Euclidean geometry, named after Euclid. He defined points, lines, straight lines, circles, perpendicularity, what he meant by parallelism, okay? And oftentimes the language that he would use and employ as he went about his business, it wouldn't really be acceptable by modern standards of doing mathematics. And sometimes he was overly verbose. He didn't have a lot of notation at his disposal. So a lot of his arguments are just long, flowing narratives describing every aspect of things, and honestly, sometimes very few pictures to accompany the argument, which is interesting, okay? He tried not to use algebra. He only used it whenever possible. He tended to want to keep things in the intellectual realm and not kind of put pen to paper as far as like doing algebraic manipulations, okay? But the algebra that he did use was only in a geometric context. And what's interesting is he never used degrees for measure. He would always talk about things in terms of right angles, 2 right angles. He would talk about the sums of the angles in a triangle, adding to 2 right angles. By the way, 2 right angles would be 180 degrees. Okay. So interestingly, he mostly described things in terms of known angular entities, like a right angle, for instance, okay? Postulates, again, I would tend to call these axioms, but he called them postulates, okay? These are basically the self-evident truths of Euclid's system, and he only started with 5 of them. Again, I said there were 23 definitions of things that he defined: point, line, etc. But these postulates were like the self-evident truths of his system of geometric thinking. And what were the 5 postulates? Well, some of them you wouldn't argue with at all. But ultimately, most of the postulates are things that you could build using a compass and straight edge. Okay? But there's one that was particularly controversial, and I really want to hone in on that rather than focus on the other four, which most of you would have no issue with at all. The fifth one was the one that's been the subject of a lot of controversy. It's called the parallel postulate. How many of you have ever heard of that before? Okay? Parallel postulate is basically encapsulated in that picture that's sitting right there. And essentially what he said was, suppose I have two lines, and then I have a transversal line, a line that kind of cuts through both of them. And suppose I look at the angles on one side of that transversal interior to those two lines. And the parallel postulate said if those two angles, alpha and beta, sum to less than two right angles, then those two lines will eventually meet on that side of it, on that side. Does that make sense? So if alpha plus beta right there was like 120 degrees, what Euclid was saying is eventually those lines are going to do what? Well, they're going to hit one another. Does that make sense? They're going to intersect on that same side. Now, does that seem like something he ought to assume? You think he ought to assume that that's true? By the way, there's lots of things that are actually equivalent to this, turns out. It's not obvious on its head, but for instance, have you ever heard someone say, you probably heard this in high school, suppose I give you a line and a point not on that line, then there is exactly one line through that point parallel to the beginning line. You ever heard that one before? Line, point not on that line, there's exactly one line through that point parallel to the given line. That's called Playfair's axiom, okay? And it turns out that's equivalent to the parallel postulate, the thing that Euclid just articulated. And there's lots of other things that are equivalent to it. For instance, the angles in a triangle adding up to 180 degrees or adding up to two right angles. Turns out that's equivalent to the parallel postulate. This is why it caused controversy. Though that seems like a lot to assume. Does that make sense? Assuming at the beginning without proof that the angles in a triangle add up to 180 degrees, that seems like a lot to assume. And so there's been a lot of controversy surrounding that fifth postulate. So everything that is built by Euclid in his Elements assumes these five postulates, the 23 definitions, and we're going to look at some common notions as well. But the one that is the most controversial is this parallel postulate, and that's what this picture encapsulates. Okay? Then common notions. Okay? The common notions are not necessarily specific to geometry. They're really meant to be self-evident. Okay? So like here's an example of common notion number 4. Things which coincide with one another are equal to one another. Okay. I mean, does that seem overly, does that seem like overly controversial in terms of assuming that? No. So the common notions are things that, yeah, we would all just sort of accept, but they're not necessarily mathematical in nature. Okay. So to accept Euclid's propositions, you must be satisfied with the preliminaries. Now, remember, the one sort of thing that's dangling out there and you're kind of like, uh-oh, is that parallel postulate thing, okay? And it turns out that it took a couple thousand years to realize this, but it turns out you could throw out the parallel postulate and actually get a completely consistent geometry without it. In fact, you could assume the opposite of the parallel postulate and still get a completely consistent geometry, but that took about another 2,000 years of thought. What people did for a long time was they tried to get rid of the parallel postulate and prove it from the other things. Does that make sense? So that it was no longer a baseline assumption. But then no one could do it. They were like, why can't we prove this thing? And the answer is because you can get a completely consistent geometry without it. Okay? For instance, doing geometry on the surface of the Earth is not Euclidean geometry. It's curved. Do you know what I'm saying? Euclidean geometry is all flat planar geometry. Everything is totally flat, okay? But it took a couple thousand years for us to realize that the parallel postulate wasn't something that we needed in order to get a consistent geometry. Okay, let's just talk a little bit about some of his early propositions. Oh, by the way, I want to pause right here. So any questions so far? Questions? Any questions? Okay. Some early propositions. He talked about angles produced by triangles, and in particular proved pretty early on that the sum of the angles in the triangles add up to 180 degrees. He had some clever arguments for why that happened to be true. He actually needed the parallel postulate to prove that, though. And it seems like Euclid himself was slightly uncomfortable with assuming the parallel postulate because he waited like 29 propositions before he actually used it. So he wanted to see how much stuff can I actually prove without the parallel postulate before I can't go any further. And it turns out he proved 28 things. And so the interesting thing is those 28 things that he proved from everything other than the parallel postulate, those things will be true in any system of geometry you happen to look at. Does that make sense? Like whether you assume the parallel postulate or not, because they're independent of the parallel postulate. Okay? Proposition book 1, number 20, says that any two sides of a triangle are together greater than the remaining one. That seems sort of obvious, right? Sometimes in mathematics, we might call that something called the triangle inequality, namely that it's obviously walking from one point to another point along a straight line is going to be shorter than going along the other two legs of the triangles. That sort of makes sense geometrically, right? But it's in this argument particularly that you start to realize that he's maybe assuming things about betweenness and inside and outside. He's starting to get a little bit loose with his language. And it becomes clear that there's probably some things that he should have assumed, at least in terms of definitions and the system he was working in, that he didn't really rigorously articulate. There's been several attempts to patch up the elements later. Sets of axioms numbering close to 20. There were some logicians that did that. Later on, even in the 19th and 20th centuries. And just the rigor, while very good and sophisticated for the time, wasn't quite there. It's in this proposition that starts to become very clear. Again, I want to reiterate, though, that none of his propositions are actually false. It's just he didn't really know he was assuming certain things, it seems. Does that kind of make sense? Okay. Congruence was something he proved pretty early on, congruence of triangles, and he did this completely through construction with straight edge and compass. He showed that, he showed the side angle side. You guys know that version of congruence, right? Side angle side. He showed that if